Interesting. You're like, those are different answers. Well, no, those are not different answers. They just look different. If we make this, right, let's let k plus 1 equal to j. All right? And this is the sum, j equals 1 to infinity, of minus 1 over j, x to the j. But j is just a dummy index of summation, so you can change it to k. And as you can see, those are the same answers. The meaning of k was different in the different answers, but you should understand it's just a notation to encapsulate a certain infinite series. K on its own doesn't have any independent meaning. It's a dummy variable of summation. It's the same idea if you have a definite integral, right? And you're, say, integrating. I mean, maybe you guys, I don't know if you guys have thought about this or not before, but you should think about this. It's actually important to applications and things. Like if I have the integral from, say, 0 to 1 of f of x dx, that is equal to the integral from 0 to 1 of f of t dt. It matters not what I call the variable of integration. Those are the same number, right? In the same way, you can change the letter that's encapsulating the infinite sum, and it doesn't change the infinite sum. There's a substitution of variables we can make. All right. So I should show you the proof of Lagrange's formula. I'm going to try anyway. Do you guys have any other questions while I'm finding that? I've actually answered all the questions that you guys actually had for me, right? I think. You have one more question. Go for it. 12.5, number 33. All right. So I threatened you guys that I would actually give you a link to this last time. I haven't done that yet. I will as soon as I can think and remember to do it. I'm not working at full power at the moment, you guys. You may have noticed I'm slightly beleaguered. Come on. Hey. Let's see here. Let's see here. Where was I? I'm trying to find the. There we go. Come on. It won't. That's not cool. Well, I hope it goes to what I want it to, because it's not letting me hit the sources button right now. We don't go to Vines or something here. Come on. Uncool. All right. My last best hope. I don't think it's on Vines. It's probably on the VGA. I have an adapter somewhere in here. Come on. Okay. So that's the theorem we're gonna prove here in a second. But first, your number 33 from what section? 33 from what was it?
Chapter 5.
Oh, it's 1 over the square root of 82. Well, so 12.5, we're asked to estimate the error in the partial sum, right? So this is an alternating series. So it's you know, we have the theorem, the alternating series estimation. So basically, here's the theorem that the sum, the nth sum minus the sum k equals 0 to infinity of minus 1 to the k, not over something, minus 1 to the k times b sub k is less than or equal to b sub n plus 1. That's the alternating series estimation theorem. And so you're asked for S80. You know, you're asked to bound the error. So this is the error in Sn. So like S80 is error bounded by B81, which is 1 over the square root of 82. Which is why the answer key has about 0.11 Square root of 82 is about 9. So 1/9 is about 0.11. That's why the answer is what it is in the back of the book. But yeah, this one, to me, this is the low-hanging. If I'm asked a question about estimation for an alternating series, I can answer those. It doesn't matter how sleepy I am. But you have questions in 12.6 which are based on using Lagrange's formula, or the remainder, which is a slightly more it's a more sophisticated tool. Let me show you how it goes. Sorry, guys. So, come on. Well, this thing is just, it's all kinds of messed up today. It won't, I hate touchscreens. Remember we used to have buttons? Remember buttons?
Yeah.
Switches? Star Trek. Oh well, I was trying to turn off the lights so this is easier to look at, but oh well, we can't do it. All right, let me accept my fate and talk through it with you guys. So here's the deal. Taylor's theorem with Lagrange's form of the remainder. If f has k derivatives, and this is probably a slightly different version than the one the book has. I may or may not go through the proof the book has, depending on whether or not I can actually think thoughts this week. Remains to be seen whether I can think this week. Anyway, so if you have a closed interval and the boundary of the interval is a and b, what I'm saying is either the interval is a to b or it's b to a. But it could be, I don't know which one's larger, which one's smaller, generally speaking. You could go either way. But in any event, if a is one end of the closed interval and b is the other end, then f of b is equal to the kth Taylor polynomial at b plus the remainder at b. Well, that's just essentially the definition of the remainder. But so this kth Taylor polynomial is sum j equals 0 to k of this. And so we're centering the Taylor polynomial at a, and then this remainder term at b, where RKB is this, that's the kth remainder. Moreover, there exists a c in the interior such that the kth remainder at b is just equal to the value of the k plus 1th derivative at c divided by k plus 1 factorial times b minus a to the k plus 1. Now I think basically what your textbook has is he has a equal to 0, all right, and b equals to x. If you look at the one I stated over here, basically if you look in the textbook in 12.6, it's the same theorem. It's just he has like a equals to 0 and b equals to x. And so x is playing the role which b plays here, and the c is just, the c is again some number between x and 0. All right, so let me talk to you about the proof. So it's we've already proved, in fact, that the kth Taylor polynomial has the same value, slope, concavity, etc. as the function at the point A. What's deep about this theorem, like I say here, is the existence of C. This is a generalization to the mean value theorem. So here's the proof. I follow a proof which is I got from Ash's real variables, Robert Ash. So I mean, it's a slight adaptation of his proof, but more or less the same. So I'm basically saying, okay, you can define this value m to be whatever m you need to make this equation true. You can do that. I mean, you can calculate these derivatives. It's given to us. We can do that. And so this defines m uniquely. All right? I could solve this for m and say m equals blah, but just to the point, I want m to have this relationship between f and its derivatives. Then what we do is replace the variable a with a variable t in the equation that defines m. So instead of putting a here, I put t. I mean, instead of putting b, I put t, rather. I'm sorry. I've lost my place here. Well, he says, oh, I'm sorry, define g by g of t is equal to, subtract that to the other side, right? Put that on the other side. I've got minus f of b plus f of t plus f prime of t times b minus t, dot, 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 like that. Now, this is just a definition. So far, you can't, I mean, you can argue with me, why would I make such a definition? I'll show you why in just a second. This is something I expect to be able to use Rolle's theorem on, right? If I plug in t equals to b, what do you get? Yeah, you get 0. So like g of well, that's not actually the point, but you can differentiate, right? If you differentiate, come on, I'm sorry, I showed you, I just mentioned that. G of b is 0. What's g of a equal to? That's the other thing. G of a is also 0 by the construction of m. G of b is 0, g of a is 0. That means I can apply Rolle's theorem, right? Remember what Rolle's theorem says? It says if the initial and final position of something is 0, then its y velocity somewhere had to be 0, right? It starts and stops at the same point, then somewhere there was a turning point, placed with 0 y velocity. And so I'm trying to use Rolle's theorem. G of b is 0, g of a is 0, essentially by the definition of m. See? Sneaky, but true. And so then all you got to do is calculate the derivative of g. Well, the derivative of g is just a straight up calculation. You just differentiate the formula term by term, and it gets you to this wonderful formula, which is b minus t to the k minus 1 over k minus 1 factorial, the kth derivative of t minus m, where I used that we can simplify factorials. We also, sorry, what do I know? I know b minus t over k minus 1 factorial is not equal to 0. Why is that? Right. So then what's the point here is we can apply Rolle's theorem, right? Okay, so this shows that g is differentiable. So g is differentiable on the closed interval a to b. G of a is equal to g of b is equal to 0. Therefore, there exists some c between a and b which has g prime of c equals to 0. So I set this equal to 0. Here I'm arguing that that can't be 0, right? So it follows that this must be 0. In other words, there has to be some c such that the kth derivative evaluated at c is equal to m, and then which shows that m is equal to the kth derivative evaluated at c. And if you go back to how m was defined, that gives us Lagrange's formula for remainder. So if you actually go back and look at the proof of the mean value theorem, it's exactly the same thing. But the difference is here what we're doing is we're studying replacing the function with its kth Taylor polynomial, with its nth Taylor polynomial. You look at the difference of the function in the nth Taylor polynomial, you apply Rolle's theorem, it gives you the existence of this c. And it just so happens that because of the construction, because of the way the nth Taylor polynomial is constructed, it gives us this particular estimation, this particular error. I mean, if you go back to here, if you see, if we have that, if we have that the kth, we have that the kth, how to say this? Well, I'm going to shut up. I think I'm out of time. So, but anyway, I may feel guilty and. What's that? No. I mean, tomorrow's quiz is about convergence and divergence.